straight into that. So this is joint collaboration with my student Johannes, who did all the lean proofs of that. And we all do know SSA form, and there's this classic dominance property that we all love and hate. So each use of a variable must be dominated by its definition, right? And dominance, this whole concept of dominance in SSA form underpins a wide array of analyses and transformation. But there's a catch. For dominance, it's derived from control flow. So we need this control flow graph, right? So if you don't have a control flow graph, it's kind of debatable what the dominance actually means. So this whole concept of dominance in SSA is only well defined for first order control flow graphs. So what do we do about higher order functions? So with this whole concept of dominance, there are two problems that I'm going to elaborate a little bit more in a minute. First of all, dominance is imprecise. And second, dominance is undefined for higher order code. So control flow overapproximates data flow. And I have this a little example here with two nested loops. Here's the dominator tree of this thing. And we have two nested loops. We have this outer loop with this header hi that introduces this induction variable I1. Then we have nested inside of that this inner loop with this header hj that has this induction variable j1. And let's say we want to do some kind of loop transformation. So let's say we want to, let's say, peel the outer loop. And in order to pull that off, we have to specialize this phi I1 and to specialize that to the first phi argument 0, right? Now, if we want to unroll the loop, we have to specialize this whole loop with the phi I1 using the second argument of the phi j2. Now, here's the problem. If we look at the dominator tree, we can see that the dominator tree tells us that the inner loop hj kind of hangs, has a dependency hi, so this outer loop. But as a matter of fact, this inner loop doesn't actually use anything that the outer loop is defining. So this dominator tree shows a false dependency. So in order to peel or unroll the loop, we don't actually have to touch the inner loop in this example. So here's problem 2. So let's say we are writing some kind of higher order program, such as we want to pass to a function eta some function f that we want to iterate. So we want that f0 of x is x, and f1 of x is f of x, and f2 of x is f of x, and so on and so forth. So we can easily write this down in a functional programming language such as OCaml. So here we have this function eta that takes this function f as an argument. Here we get the arguments n and x. And now what we can do with this eta function, for example, we can successively use this eta function with partial application to build addition, multiplication, power, and then compute 3 by the power of 5. Now, we don't have an explicit CFG here. We're passing around functions all over the place. So this property, every use must be dominated by its definition, kind of loses its meaning here, right? So we can only represent this program in SSA form in a control flow graph if we are going to lower that with some kind of closure conversion. And if we are down that rabbit hole, then the closure converted program looks really convoluted, and it's really difficult to reason about that and do any meaningful transformations in this state. Now, folks that are building compilers for functional programming language, such as SMLNJ that we've seen in this talk earlier, so they're using as an IR something which is rooted in a lambda calculus, and they typically don't talk about dominance. What they are usually doing is they have a syntax tree, and we are just relating uses to the definitions just by the syntactic scoping of the program. However, the scoping is too rigid, right? So for example, let's say we have this function g of y that is nested inside of f of x here. But we can see that there's actually no reason for this function g to be nested inside of f, right? So this means if we naively beta reduce f, we would end up with a copy of g. So in order to fight that, we would first need some kind of phase that hoists g out of f. So usually it's called some kind of block floating, and then we are good. There's also some kind of the reverse problem. So let's say we have this function f of x of y. Okay. Now we're seeing here's one call fz1 and this other call fz2. So we may come up with the idea to specialize f with z. But now we have to be super careful where we place this new specialization because we're using this variable z here. So we actually have to make sure that this new specialized function that we're creating here is placed inside of G. Now as a little recap of what we've talked so far. So for control flow graphs in SSA form, we have as a structural foundation dominance. And we're using basic blocks all over the place. We don't worry about syntactic scoping or anything like that because this dominance property tells us whether the use of a variable is kind of makes sense. The downside of that is that we at least directly cannot support higher order functions. If we use some kind of variant of a lambda calculus, we have an explicit scope nesting, which means that we are not scopeless. So we constantly have to fight the scoping, but we do have support for higher order functions. Now in our work, we introduce this lambda graph or lambda G, which is a lambda calculus, so it supports higher order function, but it's also scopeless, so all those functions are floating around just like basic blocks in a control flow graph. Now the question is, what kind of structural foundation do we use? So dominance is out of the window since we want to support higher order function. What we use instead is what we are calling free variable nesting. I will explain that later. But first, let's have a look how we can actually represent an SSA form program in lambda G. So we're using this correspondence between static single assignment form and continuation passing style to translate that. Here you can see the original SSA form program, and here you can see the program in lambda G. You can see that each and every basic block here becomes a little function, right? And all those functions here, they are just like basic blocks in a control flow graph. They are not nested inside of each other. They are just like a flat kind of structure. And each function has a label. Then we have a lambda, and then we have a list of parameters, there's only one variable. If we want to have more parameters, then we have to use a tuple. And in order to identify the variable, we use the same label as the function. We just put var in front of that. So var f0 means this thing, and var f1 means this thing. Since this is a continuation passing style where we are making the return continuation explicit, so here we have like just magically this return instruction there. But what we can see here, we are just using this red variable over here. And this is a major feature of lambda G, that we are just using this variable here that has been declared over here, just like we would do that in a CFG with basic blocks, but it's not nested. Another thing is what becomes with those phi's here. So we can see, for example, here this loop header hy. This phi thing becomes a parameter of this function here. And this argument 0, we are passing that. So this goto just becomes a function call. And we are passing this argument as argument to this function. You can see how this plays out in this other recursive call where we are passing J2 to this loop header. Now, the cool thing is if we want to do some kind of loop transformation, such as loop peeling or loop unrolling, this just becomes beta reduction. So if we want to peel the outer loop, we just have to beta reduce hi0. If we want to unroll the loop, we just have to beta reduce hij2. Now the question is, we now have this soup of functions. How do we recover some kind of nesting for that, such that all variables are properly scoped? And first of all, if we have a function g that uses the variable introduced by f free, then obviously g must be nested inside of f. So if we would translate that to OCaml, we would see that g actually is nested inside of f such that it can make use of this variable over here. Nesting is transitive. So for example, here we have this function g that uses the variable of f. So f nests g, but h uses this variable g that g introduces, so g nests h. So this also means that f nests h, so nesting is transitive. Syntactically, we can write down nonsensical programs. For example, we can have a program f that uses the variable of g, and a function g that uses the variable of f. And this is nonsense, right? We can't come up with some kind of scoping, nesting. We can't translate that to OCaml because we kind of have this contradiction here. And this is the nesting property. Nesting must be antisymmetric. And this replaces the classic SSA dominance property in our framework. Yeah, and in fact, in the paper, we prove that if a lambda G program is well typed, and we have a situation where F nests G nests H, that this implies that G dominates H in the corresponding control flow graph. The reverse does not necessarily hold, so this means that nesting is more precise. Since free variables are all over the place, and parsers can mutate the IR freely and query free variables at any time, we have this incremental free variable analysis. So at any time, you can ask an expression or a function for its free variables, and they are lazily computed on demand. And once we have the result, they are cached and memorized per functions. And then when later on asked the same question, then we get the answer in constant time. If we mutate the IR, we have to invalidate the caches. This is also implemented quite cheaply by basically just bumping some integer. And this whole framework with free variables, you don't have to rescan globally. You don't have to do a manual reanalysis. You just ask for the free variables, and you get the answers transparently, as opposed to dominance information in SSA, where you change the CFG, and then you have to recompute the dominator tree, right? So here, you just ask for the free variables, and so you don't have to worry about that. Beta reduction in our framework uses this free variable analysis to pull that off. And in particular, we don't need any kind of block floating. We are only specializing expressions as needed. And the gist of it is that we maintain a set of variables that we want to substitute, and we skip substitution when the intersection of the free variables of the expression that we consider for substitution and the set of the variables that we want to substitute. If this intersection is empty, then we don't do anything about that and continue. All right, here's once again the double loop example. Here we can see the dominator tree. And based on this concept of free variables, we can derive a data structure that we call the nesting tree. And you can see the nesting tree correctly identifies that both loops kind of live side by side because they don't depend on each other, as opposed to what you see in the dominator tree. Once you have the nesting tree, you can translate this program into a explicitly scoped language, such as OCaml, what you can see here. And you can also see those dotted lines. These are the dependencies of the functions at the same level, which basically tells us in which order we have to place those local functions in our OCaml program. Those dependencies might be cyclic, which means that we have to use letrec. Here we change the program slightly. And this time around, the inner loop actually does depend on the outer loop. You can see that the nesting tree changes and mirrors this. Almost looks like the dominator tree, with one exception. This is just how the free variables play out. But lambda G is not only limited to continuation passing style. It doesn't care whether you want to use CPS or direct style. So back to our example with this eta thing, we can translate that to lambda G in a straightforward manner. And here you can see the forest of nesting trees, how this can be computed without any form of control flow or dominance whatsoever. We evaluated that in our research compiler Mimia, which generalizes these concepts that I talked about for dependent types and other binders. So for example, if you have a dependent tuple type, this is also just a binder like a function, and those concepts work for those things just as well. And for all those things, computing free variables, beta reduction, or computing this nesting tree, we have n-log-n scaling using our data structures. Only for very pathological cases, if you have hundreds of deeply nested loops, the performance degrades. But this doesn't really happen in practice. So for example, in the whole SPAC 2006 benchmark, the max loop level is 22. So here you can see how different concepts map to lambda G from CFG with SSA form. So we've already discussed that both functions and basic blocks are just functions in lambda G. Function parameters, phi functions, are lambda variables. Function calls and jumps are just applications. Function call arguments or arguments to phi functions are arguments to this application. All those things such as function inlining, loop healing, loop unrolling, or any kind of CFG specializations are beta reduction. We talked about this SSA dominance property is now superseded by this nesting property. The concept of dominance kind of mirrors free variables. The dominator tree, if you need that, you can compute the nesting tree instead. There are some extensions to this dominator tree, such as a DJ graph, or if you're looking at the whole program, you typically complete a call graph. You can all do that with a nesting tree. And if you look at the sibling dependencies and compute this, then this kind of maps to a loop tree or call graph with STCs. Directly recursive function or natural loops map to direct recursion in lambda G, mutual recursive function or irreducible loops map to mutual recursion in lambda G. Also another thing, critical edge elimination kind of generalizes to eta expansion. Didn't have time to talk about that, more on that in the paper. So the takeaway is that nesting is a relaxed form of dominance, and we replace control flow dominance with a data flow notion of nesting built on free variables. It's more precise because it directly tracks data dependencies and not control flow. It supports higher order, well-defined where dominance is not, and it's practical. We have this incremental free variable analysis where we're caching the results, log linear in practice, and constant time access if those analysis information is already in the cache. So thank you very much.
Thank you, it's very interesting. So you mentioned theorem there about nesting and dominance. Have you proven it? And if yes, if it's paper proof or mechanized proof?
So we've proven that nesting implies dominance, but not the other way around. So I didn't caught the second part of your question. What was it?
If the proof is paper proof or mechanized proof?
It's mechanized proof. We've done that in Lean.
Hello. So I have a question relating this work to what MLIR is doing these days. So the MLIR these days have like basic blocks with arguments inside, and those have kind of replaced the traditional phi nodes. Is this something similar? Because it seems very similar to me.
Not really. So in MLIR, they're using block arguments, which kind of plays in this whole story, SSA, CPS. But other than that, MLIR is not really higher order representation. They do have those regions, but once they have those regions, they kind of going this nesting route, what you do with a typical lambda calculus. And then inside of those regions, they're computing a dominance tree, and then it kind of directly hangs in the dominance tree of its parent scope. But it's also an overapproximation, because it might be the case that the region in MLIR doesn't have any free variables at all, so it really should sit right at the top, but it's not, it's just sitting there. So I hope this answers your question.
Okay, one more while the next speaker sets up.
Just wondering if there's anything to do with the Brownian index, since it's something like SSA for the lambda calculus, and a greater index may imply dominance.
Sorry, I didn't understand your question. So you're talking about the Brown indices and how, so I mean, in the end of the day, it's a matter of how exactly you want to represent your variables. So we, in the end of the day, have a named representation, but you could totally apply that with De Bruijn indices. It's just that we are also working with a mutable representation, which rules out many of the more other fancy representations to represent names. And the other thing is that with De Bruijn indices, because we're doing aggressive hash counting, you're getting both false positive and false negatives. So De Bruijn indices isn't really anything that we want to do in our representation. But I can imagine that if you're doing a different compiler design, then this should probably work out for you. All right.